T.Y.B.Sc Sem-III paper first, Physical Chemistry. I am from MGB Arts, Commerce and Science College, Malegaon City. Today we study the chapter number 1, Chemical Kinetics. Our lecture based on the topics Introduction, Concept of Reaction Rates, Factors affecting reaction rates, Law of mass action, Order of a reaction, Molecularity of a reaction. We will also see the difference between order of reaction and molecularity of a reaction. Now first see the introduction. What is the kinetics? Kinetics is nothing but the study of the rate of the reaction. It also studies the mechanism of the chemical reaction. The chemical changes occur at different speeds, may be rapid or may be slow. So this change in the chemical reaction, it is studied under chemical kinetics. For example, explosion, it comes in the rapid reaction, whereas rusting of iron, it is very slow reaction. So the study of the rate of the reaction is nothing but the kinetics. Reaction rate, the study of reaction rates, the change in concentration of reactants or product as a function of time is known as the reaction rate. Now how we can express the reaction rate? Mathematically, we know the reaction rate is nothing but the changes in concentration of reactants or products per unit time. Since reactant concentration decreases, product concentration increases. In this chemical reaction, A is the reactant, B is the product. If you want to express the rate of reaction in terms of A, we have the rate of reaction is equal to rate of disappearance of A equal to minus dA by dt. Since the concentration of reactant means A goes on decreasing with respect to time, hence the negative sign comes in the rate expression. So minus dA by dt. Similarly, the rate of reaction in terms of B will be the rate of appearance of B equal to plus dB by dt. So what is the unit? The unit of the rate will be the moles per liter per second. Now see the reaction rate. For the sake of convenience, consider the reaction. Here two colored balls, violet color or green color ball. Suppose violet color ball it is our reactant species and green color ball it is our product species. Diagrammatically, if we have to observe from left to right as the time goes on. Now start from the extreme left hand side of the diagram. Only violet color balls are present, whereas at the right hand side of this diagram, green color balls are present. It is very clear from this diagram. As time goes on, one species is converted into the another species. Second point, there will be the changes in the chemical species, means change in the concentration. At the extreme left hand side, only the reactant species are present. At the extreme right hand side, only product species are present. As time goes on, as the reaction completed, the all reactants are converted into the product. Violet color balls are changes into the green color ball. So it is very clear that the concentration of reactant gets disappear at the last of the reaction. Means concentration of the reactant goes on decreasing, whereas concentration of product goes on increasing. Hence the negative sign comes in the rate expression for the reactant and positive sign comes in the rate expression for the product. Consider the three diagrams. In the first diagram, it is a very rapid reaction, that is the explosion, whereas in the second and third, these two are the slow reactions. Rusting of iron, it takes the time of very larger time as compared to the explosion. Change in color of the tomatoes, it is also the slow reaction. So in the chemical kinetics, the restriction will be only for the homogeneous reaction and the slow reaction that can be examined in the laboratory. Now see the factors influencing the reaction rates. First, the reactant concentration. Generally, the reaction rate is directly proportional to the concentration of the reactant. Means reaction rate totally depends upon the concentration of the reactant. Higher will be the concentration of the reactant, greater will be the reaction rate. If you have to plot a graph of concentration versus time, here we have two types of the curve. One curve decreases, other curve increases. The decreasing curve it is for the reactant, whereas increasing curve it is for the product. We already know the concentration of the reactant goes on decreasing with respect to the time. Hence, its curve goes on decreasing, whereas concentration of product increases with respect to time. Hence, its curve goes on increasing. Second factor, particle size and physical state of the reacting substance. If our reactant species are present in the solid form, the smaller the size of the reactant, faster the reaction rate. For example, if we have to take the zinc dust with dilute HCl, the reaction is rapid. Whereas if you have to take the granules of zinc with dilute HCl, it is a slow reaction. The reacting species are same, but because of the difference in the particle size, the reaction will be slow or reaction will be fast. So it is generally observed that smaller the size of the reactant, faster the reaction rate. Next, in the presence of the light, reactions occurs rapidly. Such reactions are called as the photochemical reactions. And if our reacting species are present in the form of the liquid, the reaction is also fast. From this diagram, we can clearly observe change in the particle size, reacting species, the effect will be on the reaction rate. In the first diagram, it is the slow reaction steel nail in oxygen, whereas steel wool in the oxygen. In the second, it is the fast reaction because of the smaller size of the steel wool. Next factor, it is the temperature. Rate of reaction increases with increase in temperature. Higher will be the temperature, greater will be the rate of reaction. Fourth factor also will be there, that is the catalyst. The presence of catalyst also affect the rate of reaction. Rate of reaction increases because of the presence of catalyst. See the law of mass action. What is law of mass action? The statement will be the rate of any reaction at any instant is directly proportional to the product of concentration of reactant involved in the reaction. What is law of mass action? In the rate expression, that is directly proportional to the product of concentration of reactant involved in the reaction. We cannot consider the concentration of product. We consider only the concentration of reactant. See in the first example, in chemical reaction, A gives the product. So rate is directly proportional to the concentration of only A. Whereas in the second example, 3A gives the product. Rate is directly proportional to the concentration of A power 3. The coefficient of A becomes the power in the rate expression. The coefficient of A is the 3. It becomes the power in the rate expression A cube. In the third example, A plus B, it gives the product. The rate is directly proportional to the concentration of A as well as concentration of B. The product of concentration of A and B. Last example, A plus 2B gives the product. The rate is directly proportional to the concentration of A, concentration of B power 2. The coefficient of B becomes the power in the rate expression. Now see the order of reaction. It is an experimentally determined quantity. It is obtained from the rate equation applicable to the reaction. It is defined as it is the sum of the powers of the concentrations of the various reactants involved in the rate equation. It may also be defined as the sum of all exponents to which the concentration in the rate equation are raised. On the basis of order, we have the terminology for the reactions. It may be first order, second order, zero order or third order. If the rate expression contain only one concentration terms, the rate is equal to in the first rate equal to K concentration of A. Since the A contains only power 1, hence it is the first order. In the second example, second equation rate equal to K into A square. Power here concentration of A consists of the power 2. So this power 2 represents the second order reaction. In the third, rate equal to K into concentration of A contains the power 0. A power 0 is nothing but the 1. So K into 1 becomes K. Means this rate expression does not depend upon the concentration of A, hence it is the zero order reaction. The given example, what is the order? NO plus O3. It gives the NO2 plus O2. So here we have to observe the nitric oxide, its a reaction with the oxygen. The reacting species here 2, NO plus nitric oxide plus O3. So what is the order? Obviously the order will be 2. Now see the example how we can express the reaction rate of the certain reactions. So we already see there are two rates in terms of A, in terms of B. So rate of reaction in terms of A will be negative, rate of reaction in terms of will be positive. Note that at equilibrium these two rates becomes equal. Means at equilibrium rate of disappearance of A becomes equal to rate of appearance of B. Hence minus dA by dt becomes equal to plus dB by dt. Now consider the reaction. Hydrogen plus iodine, it gives 2 times of HI. It is the homogeneous reaction because all are present in the gaseous phase. If we want to express the rate in terms of changes is in the concentration of reactor means hydrogen and iodine, and changes in the concentration of the product means HI. Note down here the product contains the coefficient 2. So this 2 goes to the denominator in the rate expression. Second point, for the reacting species, the negative sign comes, whereas positive sign comes for the product species. Hence, the rate equation becomes rate is equal to minus d of H2 by dt equal to minus d of I2 by dt equal to 1 by 2 d of HI by dt. This rate may also be expressed in terms of whole numbers. Because means if you want to eliminate the 2 in the denominator, simply we have to multiply overall this equation by 2. So after multiplying by 2, this 2 eliminate in the denominator for the product species. So first we will write the positive term. Means the product species comes first. Rate equal to plus d of hi by dt equal to minus 2d h2 by dt equal to minus 2d of i2 by dt. For this general reaction, we can clear all the concept. A plus B gives C plus D. Here small a, b are the coefficient of A and B, where small c and d are the coefficient of product C and D. And we clearly know the coefficient of the species goes to the denominator in the rate equation. So rate equal to minus 1 upon a d of a by dt equal to minus 1 upon b dv by dt equal to 1 upon c dc by dt equal to 1 upon d of concentration of d by dt. So in this way we can express the rate in terms of changes in reactant and product concentration. Rate law. The rate law expresses the reaction rates as a function of reactant concentrations, product concentrations, and temperature. It is experimentally determined. For a general reaction, A plus B gives the C plus D. The rate law is nothing but rate equal to K, concentration of A power n, concentration of B power n, where K is the proportionality constant, A and B are the concentration of reactant, M and N are the, it represents the order of the reaction. And we already know what is the order ki definition. What is the definition of order? It is the sum of powers of the concentration of the reactants involved in the reaction. So if we have to add m plus n, it gives the order of that particular reaction. So how is the rate law determined experimentally? The procedure based on first one, measure initial rates. Second, use initial rates from several experiments to find the reaction order. From initial rates, you have to find reaction order and then calculate the rate constant. The order of reaction, it is very clear. Now see the properties of reaction orders. Reaction orders cannot be deduced from the balanced chemical equation. We already see it is the experimentally determined quantity. Reaction orders are usually positive integer or zero. Reaction orders can be fractional. Now determining the reaction order, in this reaction, if we express the rate equation, rate equal to K, concentration of O2 power n, concentration of NO power n. What is M? M here is 1, N here is 2. If we have to add M plus N means 1 plus 2, the order will become 3. Now determining the rate constant. The rate constant K is specific for a particular reaction at a particular temperature. The unit for K depend on the order of the reaction and the time unit. Now see the molecularity of a reaction. It is defined as The number of reactant molecules that are involved in elementary step represents the molecularity of an elementary reaction. Elementary reaction means the reaction that completed in a single step. For complex reactions, it consists of two or more elementary steps. For complex reactions, the rate determining step decides the overall rate of reaction. If only one reactant species are involved in the reaction, that reaction is called as the unimolecular. If two molecules are involved in the chemical reaction, it is called as the bimolecular. Similarly, trimolecular or termolecular if contain the three molecules. Now see elementary reactions and molecularity. Individual steps are nothing but the elementary reactions. The elementary steps are characterized by their molecularity. So hence the molecularity is nothing but the number of reactant species involved in the step. If we consider this reaction occurs in the two steps. In the first, O3 gives or decomposes into O2 plus O. Only one reactant are present, hence it is the unimolecular. Whereas in the second reaction, it contains the two reacting species, hence it is the bimolecular. Termolecular elementary steps are rare. The rate determining step of a reaction mechanism. All the elementary steps of a mechanism do not occur at the same rate. Usually one step is much slower than the other. This step is called the rate determining or rate limiting step. The overall rate of reaction is related to the rate of rate determining state. That is, the rate law for the rate determining state, that is RDS, represents the rate law for the overall reaction. RDS represents the order. Now you can distinguish the order of reaction and molecularity of a reaction after studying all the topics. Thank you.